Hi, in this lecture we'll be covering the concept of the complex exponential. These are numbers that take the form of a e to the I theta. It has an imaginary number in the power, so we have to learn how to interpret that properly. A lot of you would have seen these things in your 2.1 course when you deal with harmonic motion, so here I go over it fairly quickly as review, so that everyone's on the same page and we can use these in our discussion for traveling waves and all the fun things we're doing this term. In introducing the complex exponential, I like to start with this very interesting mathematical phrase. This is a phrase that involves all kinds of very basic math stuff. So you got your 1 and 0, very crucial numbers, the first two numbers any mathematical person learns about. And then you have your very complex constants, also important, e and pi, as well as the imaginary number, which is, as you should know, it's the square root of -1, and your negative sign, a plus sign, and equal sign makes an equation. Lots and lots of interesting math stuff going on here, and hopefully by the end of this lecture, you would have learned all the pieces to interpret this and agree why this would be equal to one another. So, since we're discussing complex number, you might be more familiar with this form of expressing a complex number, which has a real part and an imaginary part. And you can't add them up because the imaginary part is multiplied by I, which is the square root of -1. However, we're dealing with this thing with imaginary power. So how do we interpret that? Well, let's start with thinking about if we have e to the anything. How do we deal with that? Well, we can actually use Taylor series expansion to clean it up a bit, or to look at it in some other way. So Taylor series expansion makes this going on, 4 factorial, and so on and so forth. So if we just stick in the imaginary power, then we no longer have power to deal with. We have real imaginary numbers down underneath, which we're adding and subtracting. Plus I theta to the 4th, 4 factorial, plus so on and so forth. We can clean this up a bit because we know I to the first part is I, but I squared gives us -1, I cubed gives us -1 times I, which is I to the 4th is -1 times -1, which is just 1. Knowing that, we can rewrite this 1 plus theta minus theta squared over 2 factorial plus -I theta cubed over 3 factorial plus theta to the 4 factorial, so on and so forth. So then, with that, we can group the parts with the imaginary number together and the parts without. So we can write it more as a real part and a complex part. Move it up a little bit. Okay, so let's rewrite this. E to the I theta is equal to, so collecting all the stuff that doesn't have any imaginary part to it, plus dot 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 dot, plus all the parts with the imaginary part to it, factoring that out, and so on and so forth. Well, if you remember your math, right, with power series, you might recognize that this and that equals something else that we're very familiar with. Specifically, this first part is equal to cosine theta. You can double check the calculus textbook if you're unsure. And then the second part just becomes sine theta. And this lovely statement is what we call Euler's equation. It relates a complex exponential, over here, complex exponential, with a much more familiar real part and imaginary part form. So looking at Euler's formula or equation, we can see why I chose to put the power as a theta, because in fact we're working with cosine and sine. This lends itself to interpreting the complex exponential as a more geometrical kind of thing, as a vector that points a certain direction in space with theta, and that projects a real component of cosine theta on the one side and a complex component of sine theta along the vertical axis. So then we can interpret the complex exponential as a more or less a polar representation of a number on the complex plane. You got real in the x, imaginary in the y. Of course, this currently enforces the magnitude of the vector to be 1, but it doesn't have to be that way. We can change that by multiplying it with magnitude a, which then we kind of see how this can also be interpreted as a real component plus an imaginary component give us a complex exponential. So through all these, hopefully you can see quite clearly how we can, I guess, convert the complex exponential form, which can represent any complex number, to our more familiar a plus ib kind of form. Let's switch back to the right color. So just reading this off, very obviously we have a is equal to a cosine theta, and b is a sine theta. Very, very simple stuff. To go the other way, now this is a and that's b. To go the other way to get the magnitude, we would call upon Pythagoras, so that's a squared plus b squared. And then the angle, it's the tangent of theta is b over a. Now I write this like this and not the inverse way because you have to be careful which quadrant you're in. If you're in the third quadrant, just punching in inverse tan of something into your calculator will not get you the answer. So you have to always remind yourself what quadrant you're dealing with before you pick the right theta. And there are certain names for all these things, which we can go over right now. So if you have a imaginary number, we denote as z, which we can express as either what should be obvious, the Cartesian form versus the polar form or the complex exponential form. And we have names for all these things. This here, the real part, it's the real of z. This is the imaginary part of z. This here we call the magnitude of z, or usually what we say, the absolute value. And this here we call the argument of z. So some names and vocab, but let's really quickly do a couple examples of converting from one form to the other.